So I'm Donna Nelson at the University of Oklahoma. I'm videotaping a lecture for my organic chemistry class. This lecture is lecture 4 from chapter 20 of David Klein's textbook, Carboxylic Acids and Their Derivatives. So this lecture and the PowerPoint that I've created exactly match David Klein's textbook. So I'm hoping that this makes it easier for you to study using this material. So let's look at what we're going to cover. Now it's going to be preparation and reactions of acid anhydrides, preparation and reactions of esters. So we've already finished the acid chlorides, and then in the 5th and final lecture, we will go over amides and nitriles. So this is a rather long chapter. So anhydrides can be synthesized by excessively heating a carboxylic acid. Notice 800 degrees centigrade. That is going to be very difficult to achieve in a normal lab. Gas chromatograph ovens typically at the very highest only go up to 400 degrees centigrade. So this is an incredibly high temperature. But it does work for acetic acid to generate acetic anhydride. A more practical synthesis uses the acid chloride and the carboxylate. And so remember, the carbon-chlorine bond is very reactive. Here the negative charge, pair of electrons on oxygen comes in. The pi bond moves out onto oxygen, creating a negative charge on oxygen. Then the pi bond is reformed and chloride departs. And so that is a very simple synthesis of an anhydride. That was under basic conditions, as you saw. So, given that they both contain quality leaving groups, the acid chloride and the anhydride, the reactivities are very similar, but the acid anhydrides are a little less reactive than acid chlorides, but they are nevertheless quite reactive. So here, let's look at these reactions. Acetic anhydride is often used to change an alcohol into an ester or an amine into an amide. So those two conversions can show how the anhydride can be used synthetically. And you'll notice here that we, in the reactions of, let's look at the previous one. So notice here, no acid is created, and so the pyridine is not required. Here, the reactions of acid anhydrides. Here, this is an acetic anhydride, and the reactions of the anhydrides are analogous to those of the acid chlorides. Once again, I recommend that you print this off, white out the reagents, make many copies of the sheet, and use those sheets to see if you can fill in the reagents. Use it to test yourself. Then print this off, white out the products, and see if you can, knowing the reactant and the reagent, can you predict the product? So you can make a terrific study aid from this. Preparation of esters. Esters can be prepared by SN2 reactions. You notice you are not changing anything on the carbonyl. Here you're just changing oxygen. So the base deprotonates the acid, oxygen bears a negative charge, and then that negative charge comes in and does an SN2 reaction at the methyl of methyl iodide, and iodide departs. So this is just a simple SN2 reaction at oxygen. This part of the molecule is unchanged. So notice this is under basic conditions. You can also create esters under acidic conditions. Here, use the carboxylic acid with simply methanol, and you can create the ester. The mechanism is going to be shown on the next slide, but here we have a carboxylic acid, which is in the presence of an acid, of course. And so the methanol has been protonated, and so the first step is to deprotonate the methanol. So oxygen plucks a proton off of the oxonium ion, and now that activates the carbonyl to a greater reactivity. Then the pair of electrons on oxygen comes in, does a backside attack at the carbon of the carbonyl. The pair of electrons move in the pi bond, moves out onto oxygen, satisfying the positive charge. Then, once again, methanol comes in, deprotonates the oxonium ion to give you, now you've created the methoxy group of your ester. Notice where you're going. You have to keep in mind where you're going here. So the object is to replace hydroxy with methoxy. And so now, what do we need to do to get there? We need to lose a hydroxy group. And so we've got to convert this into a good leaving group. A pair of electrons on oxygen deprotonates the protonated methanol, and so it deprotonates, leaving you with just methanol. Now this is set up as a great leaving group. This will be a nice neutral leaving group. The pair of electrons on oxygen comes in, reforms the pi bond that was here originally, and when that happens, the neutral water leaves. Then the final step is that the carbonyl is deprotonated once again using methanol. When you're carrying out, or when you're studying these mechanisms, or thinking about how to draw these mechanisms, you need to compare the reactant to the product and make certain that each mechanistic step that you draw moves you closer towards your product. A lot of other mechanistic steps could be drawn here, but they're not important, and so they're not drawn. They're not important because they don't move the reaction towards the product. Here we only want the steps drawn that actually move the reaction towards the product. This is the mechanism for this one reaction. There are a lot of other mechanistic steps that could be drawn which are not pertinent to this reaction, and so we don't care about those, so we ignore those. The mechanism is supported when the methanol is used, and the methanol is labeled, say, O18. This label is found in the methoxy group of the ester, and so that shows that this group is the one that appears there. So this oxygen belongs to the methanol. This oxygen does not belong to the acid. So at the beginning. And so these mechanisms are tested in these ways. This is an equilibrating process, and so water is removed in order to drive the equilibrium to the right. You can simply, use molecular sieves or, heat the reaction to a point where you can remove water from the reaction. Esters can be prepared by treating an acid chloride with an alcohol, just as we saw earlier in other reactions. Let's see, and notice the pyridine is used to remove, because you're going to have HCl generated, and so the pyridine is necessary to remove the hydrochloric acid byproduct. So now we have hydroxide coming in, doing an attack on the carbonyl. Here's the mechanism. So we're going to replace OR with OH, and first under basic conditions, and then a small amount of acid is used to neutralize the reaction. So hydroxide is coming in to do a backside attack. The pair of electrons in the pi bond moves out onto oxygen. Then it's reformed, and alkoxide departs. So the hydroxide has replaced the alkoxide, and so then the alkoxide deprotonates the carboxylic acid. So the carboxylic acid is generated in the carboxylate form. So let's continue the reactions of esters. The esters can also be hydrolyzed under acidic conditions. Let's look at the mechanism. However, it's totally what one would expect. So an ester being hydrolyzed under acidic conditions, the first step is going to be protonation of the carbonyl. Then remember, the overall reaction is to replace methoxy with hydroxy. So here you have the hydroxy group that needs to come in to form a bond to the carbonyl here, and that is exactly what is happening. Once this is protonated, the pair of electrons on oxygen moves in, attaches to the carbon of the carbonyl. The pi electrons move out to satisfy the positive charge on oxygen, and so then the water deprotonates the oxonium ion, and now look at what we have. We have carbon bearing 3 oxygens. Remember, this is the one that you want to lose. The product has 2 oxygens attached to it, but no methyl group. So this is the group you need to lose. So this is the group that you protonate in your mechanism. So the pair of electrons on oxygen comes out, picks up a proton. The pair of electrons in the oxygen-hydrogen bond moves back onto oxygen, satisfying the positive charge. And now this is protonated, set up to leave as a neutral leaving group. The pair of electrons reforms the pi bond. Methanol leaves as a neutral leaving group, which is a low energy process. And so then water deprotonates the protonated carboxylic acid and the positive charge on oxygen. The oxonium ion is satisfied. And so then the carboxylic acid has been generated. Esters can also undergo aminolysis to form amines. And so a pair of electrons on nitrogen moves in, attacks at carbon. The pair of electrons, let's see, that will be, I think that's covered on the next slide. Let's look and see. This favors the amide formation because these are less reactive than esters. This is the least reactive of the carboxylic acid derivatives. So if one uses excess lithium aluminum hydride, one can convert an ester into an alcohol. This reaction is analogous to that of the acid chloride. Here, so two different alcohols are produced. Note, one from this part of the molecule, and then the methoxy group that is going to be expelled. So let's look at this mechanism. It's analogous to the reduction of acid chlorides using LAH. So H minus attacks the carbonyl carbon. The pair of electrons moves out onto oxygen, generating a negative charge. Then the pair of electrons on oxygen moves back in and reforms the carbonyl, and methoxide departs. Then H minus attacks again with the pair of electrons moving out onto oxygen. So now you have attached the two hydrogens. You formed the two CH bonds that are there in this alcohol, and the negative charge on oxygen, a pair of electrons, picks up a proton from the water and forms the alcohol. So this also is a primary alcohol because you formed two CH bonds. Once again, the reduction of the ester can be stopped at the aldehyde using the diba, just like you saw before. This is diisobutyl aluminum hydride. This is less reactive, and so it's more selective, and so it will react only with the ester and not with the aldehyde. So the aldehyde, it stops at the aldehyde, and the aldehyde is left intact. So this is another reaction in which you're using a reagent that is less reactive and more selective. Esters can react with Grignards. So here we have excess Grignard. You're going to use two equivalents because you have a leaving group. So one of the equivalents will be used to replace the leaving group. The other equivalent is used to react with the carbonyl. And so, modify the carbonyl to create an alcohol. So here we have the first alkyl anion come in, attack. The pair of electrons moves out onto oxygen, then it reforms, methoxide is expelled. You have temporarily generated the ketone, then the ketone will react with the Grignard. A pair of electrons moves in, the pi electrons moves onto oxygen, forming the oxygen anion, and then you cannot expel one of these groups. None of these groups is a good leaving group, and so this is protonated to give you the alcohol. And so now this has finished the reactions of esters. We will go on and look at the reactions of amides.